In this video, we're going to look at solutions to an old Math 9 business calculus exam that I gave. This is for test 1. It covers continuity, looking at the formal definition of the derivative, finding equations of tangent lines, using certain rules to help us find the derivatives, product rule, quotient rule, chain rule. So let's go through and look at the solutions to this exam. So the first problem, looking at the graphs of f of x, answer the questions about the functions. So looking at the first graph on the left, it has a shape of an upside down parabola, and we're looking at what is f of -3. So what that's saying is, what is the y value when our x value is -3? So if we look at this, when x is -3 on the graph, I see that my y value here is 4. Now we're looking at the limit as x is approaching -3 of f of x. So we're looking at the left and the right-hand side of this graph, and as we're coming in on the graph, so the left-hand side, as I'm coming in, I'm getting a y value, getting closer and closer to that y value of 4. Same thing on the right-hand side, I'm getting closer and closer to 4. And since I'm approaching the same value on the left and the right, the limit as x approaches -3 of f of x is 4. So now we're looking at a similar graph, but this time when we're looking at it, we want to find f of -3. The problem is when x is -3, we have an open circle there. And so if you look at this, since there's an open circle here and there's no closed point above or below that value, there's no value. This is undefined when x is equal to -3. It does not exist. Now let's look at the limit here though. So if we're looking at the limit as x is approaching -3 of f of x, then we're looking at, again, what's happening as we're coming in on the graph, approaching on the left-hand side and the right-hand side. So looking at this, as we get really, really close to x equals -3, even though it doesn't exist at x equals -3, we're still getting closer and closer to that y value of 4. And so the limit as x approaches -3 of f of x is equal to 4. Looking at the third graph, very similar to the first two, it's an upside down parabola. We have an open circle, but this time we have a closed circle that is below that open circle. And so when we're looking at f of -3, it is defined, and that y value here is 1. So f of -3 is 1. If we're looking at the limit though, as x is approaching -3, so looking at the graph as we're getting closer and closer on the left of -3, notice the y value we're approaching, even though it's not defined at that value, that y value is getting closer and closer to 4. Okay, so the fourth graph, looking at f of -3. So looking at when x is -3, there's a jump in the graph when x is -3. So notice that solid circle here. At x equals -3, our y value we have is 1. If I look though at the limit as x is approaching -3, on the left-hand side, I'm getting closer and closer to that y value of 4. But on that right-hand side, as I'm coming in on that graph as getting closer and closer to x equals -3, my y value is 1. And so if my limit on my left and right do not exist, then, does not exist. If they do not equal each other, then that limit does not exist. So that limit does not exist here. In this case, notice as we're approaching x equals -3 on that last graph on the left, our y value is 4. On the right, that y value is 1, but both of those had an open circle there. The limit doesn't exist because left and right do not equal each other. But if we look at f of -3, the graphs are both approaching an open circle on the left and the right, but we have a point that's in between those two open circles. So that's where our function is defined. So when x is -3, the y value is equal to 2. So if you're in my class and you're doing the assignment where you're grading your practice exam, notice that that problem 1, there's 1 point for each problem. And so that first graph, f of -3 is worth 1 point. Give yourself 1 point if you got that correct. Give yourself 0 points if it's wrong. The second part of that graph, limit as x is approaching -3 of f of x equals 4. Again, if you got it correct, give yourself 1 point. If you got it wrong, give yourself 0 points there. And then put your score on the left-hand side here. How many you got correct? All over 10. And that's how I'll be grading your exam and passing it back. The one that you're taking in class this week. If you're not in my class, then hopefully this is beneficial for you. So this next question, number 2, we want to sketch a graph of a function f that satisfies all of these following conditions. And so we have 5 different conditions here that we want to hold true. And so answers can vary here. But as long as all 5 of these conditions hold true, then we have a graph of f. So f of -2 for part A is equal to 5. So that's saying when x is -2, I have a point at 5. We're going to put some information in here as we go, but we might have to, as I go back, or as we go further, I might have to change things. But part B says the limit as x is approaching -2. So same value here, x equals -2. It says my limit is approaching 1. And so just like we were looking at on those other examples, I know that I have an open circle here. So when x is -2, my y value is really 5, but the limit is approaching 1. So I don't know if I'm decreasing or increasing as I come in to the point on the left, but I will look at that in a minute. Part C says the limit as x is approaching 4 on the right-hand side is equal to 3. So let's look at when x is equal to 4. Our y value that we're getting closer and closer to, and we're coming in on the right, is equal to 3. So I don't know if I have an open circle here or a solid circle here. We'll come back to that again, but I know on the right-hand side, I'm getting closer and closer to this point. Part D says f is increasing on x less than -2. So if x is increasing for x less than -2, then we are rising as we move left to right, as we get closer and closer to this -2 here. And then the last part, part E, says the limit as x is approaching 4 on the left of f of x is less than the limit as x is approaching 4 on the right of f of x. So that's telling me my y value on the left as I'm coming in to x equals 4 is smaller than my y value on the right. And so my picture is a little bit off here. So erase that. That y value on the right has to be bigger than this one on the left. And so the limit exists there. It could be an open or closed circle. They will both satisfy that condition. Let's just combine our graphs. So we might have something that looks like this. So here's an example of a function f of x, the graph that satisfies all 5 of those conditions. So question number 3, we're finding the limits of the following function if it exists. If it does not exist, then we're going to show why. So when we're doing limits, we're doing direct substitution. So we're looking at the limit as x is approaching -2 of x squared minus 5x minus 6. And so we're going in here, wherever we see an x, we're going to replace it with -2. So I have -2 squared minus 5. I see an x, replace that with -2, minus 6. So -2 quantity squared, we got 4. -5 times -2, so that's 4 plus 10 minus 6. 4 plus 10 is 14. 14 minus 6 is 8. So our answer in this case is 8. Now, if we look at part B, the limit, we're looking at the limit as x is approaching -3 of x squared minus 9 all over x squared plus x minus 6. So if we go through here and we do direct substitution, which you should always start by doing that, I notice that I am going to get an indeterminate form of 0 over 0. I believe I do, but let's just show it. So I get -3 squared in the numerator, which is positive 9 minus that 9. That is equal to 0 in the numerator. In the denominator, I have -3 quantity squared is 9 plus a -3, so -3 minus 6. So 9 minus 3 minus 6 is also 0. And so we get that indeterminate form of 0 over 0. So if we get that indeterminate form, that tells us that we need to go back and manipulate what we're taking the limit of. And so in this case, I notice that we can factor both the numerator and denominator. And so let's factor that. I have a difference of squared of x squared minus 9. That factors as x minus 3 times x plus 3. All over x squared plus x minus 6. So that factors two numbers that multiply to a -6, but adds to a -1. So that would be a +3 and a -2. So that factors as x plus 3, that quantity times the quantity x minus 2. So once we factor this, notice that we have common factors in the numerator denominator. We can cancel those out. Canceling out the factors of x plus 3, we're left with a limit as x is approaching -3. So now doing direct substitution, we have -3 minus 3 in the numerator all over the -3 minus 2 in the denominator. So -3 minus 3 is -6 in the numerator, all over -3 minus 2 is -5 in the denominator. Two negatives, division makes a positive, and so our answer is 6/5. Moving to part C. And so notice here that our question 3 is 16 points. If you're grading in my class, then that first part A is 3 points. This 4 is telling me part B is 4 points. C is going to be 3 points. D will be 2 points. And E will be 4 points. Give yourself full credit if you get it correct. Give yourself partial credit if you had some clue of what was going on, but you made some errors. If you had no clue of what was going on, or if you left it blank, then give yourself 0 points. Part C, we have a piecewise function. We're looking at the piecewise function. First equation is 1 minus 2x. We're using this if x is less than -2. And we have x squared plus 1 if x is greater than or equal to -2. Well, first we're looking at the limit as x is approaching -2. So since that's the value where we're changing in our inequality, we want to show that either the left and right hand limit as we're approaching -2 is the same. And if it's so, then the limit exists, or that they're different. And if that's the case, then the limit as x approaches -2 would not exist. So if we're looking at the limit as x is approaching -2 on the left-hand side, we're choosing values here where x is less than -2. That's why I chose the first equation there. And so we'll do direct substitution now. We have 1 minus 2 times the -2. Simplifying this, we have 1, a -2 minus times a -2 is a +4. So we have 1 plus 4, which gives us 5. So limit as x approaches -2 on the left-hand side is 5. Now looking at the limit as x approaches -2 on the right-hand side, those are values where x is bigger than -2. So we're plugging that into the second equation, which is x squared plus 1. Plugging that in, we get -2 quantity squared plus 1. Well, if I square -2, I get +4, and 4 plus 1 is 5. And since our limits are the same as we come in for the left and the right, our limit as x is approaching -2 is equal to 5. So part D says, is f of x continuous at x equals -2? Why or why not? Well, in order to be continuous, the limit as x approaches that value has to exist, which we just showed it did, and that was equal to 5. F of the value that we're looking at it being continuous of, so f of -2 also has to exist. So going back into our equation of f of x, when x is -2, that tells me I'm using the second equation because x is greater than or equal to -2, it follows that condition. And so plugging in -2 into that second equation, we also get 5. And since the limit is equal to f of the value we were taking the limit, then it's continuous. Okay, so yes, it's continuous because of the conditions I just stated are all hold. So part E, we're looking at the limit as x is approaching -infinity of x squared minus 2 all over 4 minus x cubed. Okay, so looking at this, we want to look at the variable raised to the highest power in the denominator. So this is when we're looking at the limits as we're going off to -infinity or infinity of a rational function. We see that the highest power in the denominator is an x cubed. So the trick here is to go in and multiply by our fancy 1 over x cubed all over 1 over x cubed. I should state that we're doing this because if I plug in -infinity there, I get an infinity over an infinity, which is an indeterminate form, which meant I need to go back and manipulate this. If we multiply both the numerator and denominator by this 1 over x cubed, our fancy 1, then notice that we'll get the limit as x is approaching -infinity of, we would have an x squared times a 1 over x cubed. That's an x squared over x cubed, which reduces to a 1 over x, minus distributing this 1 over x cubed to the 2, we get 2 over x cubed, all divided by, so distributing this in the numerator, this 1 over x cubed times 4 is 4 over x cubed, minus an x cubed times a 1 over x cubed reduces to a 1. We're using the fact that if we are looking at a limit as x is approaching infinity or -infinity, and we have some number divided by that infinity or -infinity, that piece of the limit goes to 0. So 1 over -infinity approaches 0. That 2 over -infinity cubed approaches 0. This 4 over x cubed approaches 0. And then the -1 approaches -1. So we're getting really 0 over -1, which reduces to 0. So limit as x approaches -infinity of that rational function is 0. So on number 4, we're given a graph. It says, consider the graph of the function f of x on the interval given from 0 to 5. Part A wants to know for which values with the derivative f prime of x not be defined. Okay, so recall the derivative is not defined or doesn't exist. Another way to say that, it's not differentiable at that value at sharp corners or places where we have a vertical tangent line or where it's discontinuous. So I notice there's places where I'm having these sharp corners in here. And so this is where x is equal to 2. I have a sharp corner here when x is 3. And I have another sharp corner here when x is 4. And so the values of x where our derivative is not defined would be when x is 2, 3, and 4. Part B, sketch the graph of the derivative function, f prime. Make sure that we label the x and y axis and the unit on the graph. Okay, well, x and y axis is labeled here. So if we look at this, so let's look at that first piece of the graph where it's increasing. So notice that it's increasing here from 0 to 2. This is where our graph is going up, left to right. That's a line there, and so it's going to have a slope, the same value in between, or slope in between x equals 0 and 2. It's going to have the same slope. So let's look at some points that we can see on this graph easily and see how much we're rising and running. So notice here we have a point at 1, 0. Down here we have a point at, it looks like 0, -1. So I'm rising up 1 and I'm running over 2. So my slope is rise over run. So for this piece, my slope is rise 1, run 2. So I have a slope of 1/2 between x equals 0 and 2. So let's put an open circle here. Y value of 1/2 horizontal line here between 0 and 2. So now let's look at the piece here between x equals 2 and x equals 3. So notice here that the slope is a horizontal line. So our slope here is equal to 0. So I know from 2 to the y value of 3, open circles at 2, 0 and 2, 3, and everything in between that is on the x-axis, y is 0. Looking at this next piece in here from x equals 3 to 4, I'm decreasing. Let's look at some points that are on that and see rise over run. We're falling though. So here we have a point at, that's a 4, I believe. So that's a 3. So I have a point here at 3, 1. And here, looks like I have a point when x is 4, I have -1. So I'm falling, not to scale, but I'm falling 2, so down 2, and I'm running over 1 from 3 to 4. So M is on that piece, falling 2, so -2, running over 1. So my slope on that piece is -2. And so from x equals 3 to x equals 4, my slope is -2. So it's a horizontal line there at -2, but open circles at x equals 3 and x equals 4. Last piece, we're looking at this piece where we're increasing from 4 to 5. So we're going up. I know my slope is going to go up. It's going to be a positive. So let's see how far we're increasing. Well, I'm going from -1 to a 1. So I'm increasing 2 here. And I'm running from 4 over to 5. So I'm running over 1. My slope is 2. So I'm going to have an open circle at 4, 2, open circle at 5, 2, and a horizontal line joining those two. And so here's a graph of our derivative function of the graph of the function f of x on the interval from 0 to 5 given above. Problem number 5. Find the derivative of f of x equals x squared minus 3 quantity squared by the given using the given method. Okay, so we're gonna use the method that tells us to find the derivative. Show you get the same result for each method. Circle the letter of the one you found was the easiest method. So part A says we're going to calculate the derivative of f of x by expanding and simplifying the function first. So we're given here that f of x is equal to x squared minus 3 quantity squared. So we're going to rewrite this x squared minus 3 all times x squared minus 3. We're going to expand this. So this gives me x to the 4th minus 3x squared. Distributing my -3, I have -3x squared, and -3 times -3 gives me +9. My function f of x, by expanding it and then combining these like terms, and x to the 4th, I have a -3x squared minus a 3x squared gives me a -6x squared, and then +9. Now we're ready to take the derivative from this expanded form. We're going to use the general power method that we just learned. And so instead of using the formal definition, so we're going to bring our power down front. So that's going to give us, for the derivative of x to the 4th is 4x, and subtract 1 from our exponent. So 4 minus 1, we have a 3. Minus, bringing our exponent down, we're bringing our 2 down times the -6 in front. So -6 times 2. Subtract 1 from our exponent, which is going to be 2 minus 1. So that will give us just the x. Plus the derivative of 9. Well, a derivative of constants always 0. So our derivative function f of x is equal to 4x cubed, -6 times 2, so minus 12, and then the x. Part B says use the product rule to find the derivative of f of x. So we're going to rewrite this x squared minus 3 quantity squared as a product of those two factors, x squared minus 3 times x squared minus 3. Our first function is the first x squared minus 3. Our second function is also x squared minus 3. Remember, when we use the product rule, you're taking the derivative of the first. So I'm just going to write that I'm taking the derivative and then do it. So d dx of x squared minus 3, I haven't done the derivative yet, times the second function, which in our case is x squared minus 3, plus the first function, x squared minus 3, times the derivative of our second function. So I'm going to write d dx of our second function, x squared minus 3. Now let's go through and take the derivative of the pieces that we need to take the derivative of. And so taking the derivative of our first piece, x squared minus 3, derivative of x squared is 2x, the derivative of -3 is 0. So we have 2x all times the second x squared minus 3 plus x squared minus 3 times the derivative of the second. Derivative of the second is the same as the first because of the same values. So let's distribute the 2x to the first parentheses and the 2x to the second parentheses. 2x times x squared is 2x cubed. 2x times -3 is -6x. Plus, distributing our 2x to the second parentheses, 2x times x squared is 2x cubed. And 2x times -3 gives us -6x. Combining like terms, 2x cubed plus 2x cubed is 4x cubed. And -6x minus 6x is -12x. So our derivative function is 4x cubed minus 12x. Exactly the same thing that we got on part A. So part C, one more time taking this derivative, or at least right now. Actually, don't listen to me. So one more time taking this derivative another different way is using the chain rule. So we have, again, x squared minus 3, but this is quantity squared. So using this chain rule, so the outer function we're treating as this quantity squared. So the derivative says, using the chain rule, the derivative of the outer, so bringing down the 2, of the inner function, x squared minus 3, don't do anything to that. Subtract 1 from the outer function, that squared minus 2 minus 1 is 1, times the derivative of the inner. So let's just say we're going to take the derivative of the inner, which is x squared minus 3. So let's simplify this. So let's distribute this. Let's not distribute yet. So we have this 2 all times x squared minus 3 times the derivative of the inner piece, derivative of x squared minus 3, that is 2x. So we're going to just, let's first multiply 2x times 2. So that is a 4x times that x squared minus 3. If we distribute that 4x to the x squared minus 3, we get the same thing, 4x cubed minus 12x. Same thing we got as above. Part D, find the derivative of f of x using the formal definition of the derivative. Just set this up. You don't need to calculate it. So if I went in and was looking at using the formal definition, which I gave you here, we're looking at f of x plus h. So we're plugging in x plus h wherever we see an x. So we have x plus h quantity squared minus 3. And then we're squaring that whole thing. Minus f of x. So f of x again was x squared minus 3 quantity squared all over h. So if we expanded that out, we would get a 0 over 0. We would simplify by canceling out a like factor, which we should have of h in the numerator and denominator. And then looking at the limit as h goes to 0, plugging in 0 wherever you see an h, you should get what we had gotten from above. And right beside it. So number six, we're looking at finding the derivative using the rules that we have just learned. And so using our general power rule for this f of x equals 3x cubed to minus 3x plus 3, taking the derivative of this, bringing our power down front and multiplying it to the coefficient in front of there. So I have 3 times 3 is 9. Subtract 1 from my exponent. So 3 minus 1 is 2. So our new exponent is 2. Derivative of negative 3x is negative 3. Plus the derivative of our constant 3 is 0. So for part B, g of x is equal to the cubed root of x squared. Before we can use that general power rule, let's rewrite this radical as a rational exponent. So recall that index of our radical that goes in the denominator of the fraction, fractional exponent. And this is 2 here from the x squared, that 2 goes into the numerator. Now we can use the general power rule, bringing down our exponent down front, 2/3 x. I'm subtracting 1 from 2/3. If it's a fraction, create that 1 to have a common denominator. So that 1 I'm going to rewrite as 3/3. Let's simplify this a little bit. So I have the derivative here is 2/3 x to the negative 1/3. 2/3 minus 3/3 is negative 1/3. For my class, I'm okay with you leaving it like this. You probably, for future, would want to rewrite that, make that exponent positive. We can bring it down to the denominator. That would be x to the 1/3 power, which is the same thing as the cubed root of x. C, I could use the quotient rule to take the derivative of x squared minus 2x plus 1. All of that over x squared. Or because I'm only have one term in that numerator or denominator, I'm going to break this down as x squared over x squared minus 2x over x squared plus 1 over x squared. I'm going to use rules of exponents to rewrite this before I take the derivative. So x squared over x squared, that cancels to 1, minus 2x over x squared is 2 over x plus 1 over x squared. So now I'm still going to use rules of exponents by bringing my x up into the numerator and rewriting it to have the negative of the exponent it was down in the denominator. So 2 over x can be written as negative 2, because of the minus up front, x to the negative 1 power. Plus this 1 over x squared could be rewritten as x to the negative 2 power. So now in the form, we can just go ahead and use the general power rule. So we can take the derivative of a constant 1 is 0. The derivative of a negative 2 times x to the negative 1 power, bringing our exponent down front. Negative 1 times that negative 2 is 2. Subtract 1 from our exponent, we get negative 2. Plus, bringing our exponent down front for x to the negative 2, we have negative 2. Subtracting 1 from our exponent, so negative 2 minus 1 is negative 3. I'm okay if you leave it like that, or we could rewrite it as 2 over x squared minus 2 over x cubed. So D. Y is equal to x over x squared plus 2. It says to use the quotient rule. So the quotient rule says dy dx. Take the derivative of the numerator. I'm supposed to have student hours right now, so I'm going to kind of speed up and go through this. So taking the derivative of that numerator, I have 1. Quotient rule then says take the times the denominator minus the numerator, x, times the derivative of the denominator. Well, derivative of x squared plus 2 is 2x, all over the denominator, which is x squared plus 2. That is quantity squared. You might want to clean it up a little. This is x squared plus 2. A negative x times 2x is a minus 2x squared, all over x squared plus 2. And that x squared plus 2 is quantity squared. I can simplify by combining like terms in that numerator. And I have x squared minus 2x squared, so that's a negative x squared plus 2, all over the quantity x squared plus 2. That quantity is quantity squared. For E, find the derivative of y equals x over x squared plus 1 by rewriting it. Okay, so we're in the form here that we can use the product rule. And within that product rule, we're going to use the chain rule. So using this, let's just write what we're doing. So y prime, or dy dx, another way to write the derivative, is the derivative of the first function. So I'm going to take the derivative of my first function, which is x, times the second, which is this x squared plus 2 to the negative 1, plus the first function x, times the derivative of the second. So I'm going to write that I'm going to take the derivative of the second without doing it yet. Second function is the quantity x squared plus 2, and then that's raised to the negative 1. So derivative of the first, derivative of this x is 1, times the second. Because I didn't take the derivative of that, I'm going to rewrite it as 1 over x squared plus 2, just because I know I'm going to have to rewrite this to be the same, plus x times the derivative of the second. So the derivative of the second, I'm using my chain rule, bring down my power down front, -1 of x squared plus 2, subtract 1 from my exponent, -2, times the derivative of the inside. So my derivative of the inside there is 2x. So I have 1 over x squared plus 2. I notice I have a -1 times x, or negative x, times a 2x. So negative x times a 2x, so this is going to be a minus 2x squared, all over. So let's bring this piece, this x squared plus 2 to the -2 power, let's bring it down to the denominator, x squared plus 2 quantity squared. So that's our derivative using the rule of rewriting it using the product and quotient rule. Part F wants you to show that D and E are equivalent. In order to show that's equivalent, I'm going to need a common denominator. My LCD, I notice, is x squared plus 2 quantity squared. So let's multiply that first fraction by x squared plus 2. X squared plus 2. Fancy one. And so doing that, I would get in the numerator x squared plus 2 all over my LCD, x squared plus 2 quantity squared, minus 2x squared. So that was just getting a common denominator and rewriting it as a single fraction. I notice now that my numerator, -2x squared plus x squared, simplifies to -x squared, plus a 2 all over my common denominator of x squared plus 2 quantity squared, which is the exact same thing that we got using the quotient rule. Part 7. The revenue in dollars generated from selling X items is given by the following function. R of X is equal to 54 minus X squared over 200. So we want to find the marginal revenue, which is R prime of X, which is finding the derivative. Well, the derivative of the first 54, derivative of the constant, is 0. Notice that this gives the same thing as 54 minus, I can rewrite this if it helps you, as 1 over 200 times x squared. So when I'm taking the derivative of that 1 over 200 times x squared, that 1 over 200 stays there. Bring our exponent down from the x squared, so that 2. Subtract 1 from our exponent, we just get x. And so our derivative function is equal to -1 over 200 times 2x. But notice that reduces. So let's reduce now. 2 goes into 200 100 times. So we get -1 over 100x for our derivative function. Estimate the revenue of the 4,001st item being sold by finding the derivative of our revenue, R prime, of 4,000. So we're just going in here and plugging in 4,000 wherever we see an X. So plugging in that 4,000 where we see an X in the what we got above. We have 4,000 times -1 over 100. 2 zeros cancel, leaving us -40. So it looks like they're losing $40 when they sell the 4,001st item. So determine the actual revenue from the sale of the 4,001st item being sold. Well, we would have to look at the revenue of 4,001st item That's going to give us the revenue of selling the first item, the second, the third, the fourth, all the way up to the 4,001st item. So we want to subtract off how much we got from the first 4,000. So we're looking at the revenue of 4,001 minus the revenue at 4,000. So if you plug this in, this 4,001, wherever you see an X in our original function, this is going to equal 54 minus 4,001 quantity squared over 200 minus 54 minus, now plugging in 4,000 wherever you see an X, so 4,000 quantity squared over 200. If you look at this and you distribute this negative inside, this is going to give me a 54 minus a 54. So those are going to cancel with one another. So I'm looking at what is 4,001 squared over 200, and then minus 4,000 squared over 200. Okay, so grabbing my calculator and plugging that in, I have plugging in 4,001, squaring it, I get 80,000, negative 80,000, 40.005 plus, because that minus times that negative is positive, 4,000 squared, so that would be 16 with 6 zeros. Divided by 200, cancel out a couple of zeros. We get 160,000, something's off. So let me just plug it in, 4,000. Maybe I put 401 in the other one, squared. Divided by 200 is 80,000. Okay, that makes more sense. So this is negative 80,040.005 plus 80,000. I forgot to, had to go into that 16. So that's going to be negative 40.005, which notice is almost identical to what we got above. So compare your answers B and C, and what do you find? That they're almost identical. Hopefully you saw that doing it by taking the derivative was a lot faster and easier. That's something else that you could state there. One more question. This is number 8. So given the information about a function and its derivative function, answer the following questions. So here we're letting y equal f of x times h of x minus 4 times g of x. So we want to find the derivative of y at x equals -3. So looking at this, let's first take the derivative and then we'll go in and evaluate. So I notice when we take the derivative of f of x times h of x, we're going to need to use the quotient rule. So y prime is equal to, so f of x times h of x, derivative of the first, f prime of x, times the second, so h of x, plus the first, f of x, times the derivative of the second, so h prime of x, minus 4 times g of x, so taking the derivative of this would be 4 times, and the derivative of g of x is just g prime of x. So now let's go in and let's evaluate this. When x is equal to -3. So all we're doing is we're going in and we're plugging in -3 wherever we see an x and our derivative function above. So we have f prime of 3 times h of -3. H of -3. So f prime of -3 times h of -3 plus f of -3 times h prime of -3 minus 4 times g prime of -3. So now we're going to use our chart above to figure out what our values are. So we're looking at the derivative of f of x. So find the derivative of f of x when x is -3. So I notice that there is an error in here because we don't have an x equals -3. So I must have not corrected this. Let's change this. Let's see if this, I'm sure when I gave this to class, I gave them the corrected version. So let's try that with +3. Okay, so if we did that same thing, but with +3. So the derivative function evaluated at +3 is 4. If we look at h of +3, find your function h of x when x is 3, our y value is 0, so 4 times 0, plus f of +3. So our f of x function is here. At +3, we get 2. H prime of +3. So looking at h prime of x at +3 is -3. Minus 4, all times the derivative at +3. So derivative at +3 for the g of x function, which is over here, is 2. So let's simplify that. 4 times 0 is 0. 2 times -3, so this is -6. And then -4 times 2 is -8. So -6 minus 8 gives us -14. Part B, we want to look at j of x equal h of x over g of x. What is the derivative of j evaluated at 2? So let's just write it out first. We're going to need to use the quotient rule, which says we're going to look at the derivative of h of x times the derivative of the numerator times the denominator, so times g of x, minus the numerator h of x times the derivative of the denominator, g prime of x, all over the denominator quantity squared, so g of x quantity squared. So now let's evaluate that when x is 2. So if we look at that, we have h prime of 2 times g of 2 minus h of 2 times g prime of 2 all over this g of 2 quantity squared. So again, we want to look at our table, plug in our values. So h prime, so that's the last column. H prime of 2 gives us back 2. All times g of 2, which is 0. Then minus h of 2. H of 2 is 3. All times g prime of 2. So g prime of 2 is positive 3. All over g of 2. G of 2, which is 0, quantity squared. So I get -9 over 0 squared is 0. -9 over 0, this is undefined. C, k of x is equal to f of g of x. What is k prime of 0? So let's first look at the derivative of k of x. It's a composition of two functions, so that's equal to the derivative of the outer of the inner function times the derivative of the outer. So f prime of g of x times g prime of x. So now evaluating this, when x is 0, we have f prime of g of 0 times f prime of 0. Okay, so again, looking at our table, this time x is 0. And so let's first look at g of 0. So g of 0, x is 0, g of 0 is 1. So this is going to be rewriting this f prime of g of 0, but g of 0 again is 1. So we have f prime of 1 times f prime of 0. So looking up here, when x is 0, f prime of 0 is 3, all times 3. So we need to use the table again, f prime of 1. So when x is 1, f prime of 1 is 3. Did I do the wrong thing up here? F prime of 0, actually, I did. F prime of 0 was this -1. So it should have been -1 up here. Now f prime of 1, though, when x is 1, f prime of 1 was 3. So you have 3 times -1, which gives us -3. So in that problem, we needed to use our formulas for product rule, quotient rule, chain rule, write that out, and then use the table to evaluate it. And so that was the last problem to that old test. Hopefully that was helpful. Score up your test, what you got correct, how many points, and put your score at the top of the page. And for my students in my class, upload that written work to the Canvas assignment. And this is for my students in spring 2023.